Here are a few misconceptions that I have observed when I was marking the BI308 exam question, when we talked about statistical tests. And I want to address some of these misconceptions. So one of the very common misconceptions was that the critical value of a test is 0.05. And that's not right. What probably was meant is that the significance level, so the significance level, alpha, that could be set to 0.05 or 5%. But it's not the critical value. The critical value tells us the value of a distribution from which we then say that if the test statistic is larger than the critical value, then we think there is something wrong. But what was meant was here probably the significance level. And the significance level does not have to be 0.05 or 5%. The significance level can be any level, can be any value that you want to set, so where you say, well, if the probability is lower than the significance level, then I will reject the null hypothesis. So it does not have to be 5%. This is a very common convention, but there's no law in the universe that says it has to be 5%. So that's this one here. Bacterial cells. A lot of people have given me the example for bacterial counts on plates, and they wanted to analyze them with Ttest. And although you could, in theory, do that, it is not a good test, because what you're dealing with is you have count data here. So these are count data. And as such, these data are not continuous data. And we know that in the case of count data, we would use a Poisson distribution to look at these things. And the Poisson distribution is a variation of the chi-square test. So a t-test is not the best option to look at bacterial counts or any counts on in a certain space or time. Another very common misconception was that chi-square test can only have two categories. No, that's not true. It can have as many categories as you want. So it can have more than two categories. It's just simply, if you look at, for example, a Hardy-Weinberg example, you have three categories. You can have 100 categories. It makes it a little bit more, how shall I say, involved, but nevertheless, you can have as many categories as you want. Now, with a t-test, on the other hand, you can have only a maximum of two categories of where the independent data are comprised of a maximum of two categories. If you have more than two categories, you would choose a different test, in this case an ANOVA, but for a chi-square test, you don't have this restriction. Some people presented me with standard deviations or confidence intervals or correlation coefficients, and they use these as examples for statistical tests. And these are required elements to perform a statistical test. Required elements, but they are not per se a statistical test. In a statistical test, you compare two or more sets of data with each other or with expectations or something like that. Whereas standard deviation, confidence interval and correlation coefficients, these are descriptive statistics. So this here is all descriptive statistics. It is not a test. And even if you say the Pearson correlation coefficient R equals 0, yes, that might be a sort of a null hypothesis, although when you look at the correlation between two continuous variables, and that is what it is, you would formulate the null hypothesis in a different way. You would formulate the null hypothesis that the gradient actually is 0. The correlation coefficient, that is usually totally irrelevant. What you would usually formulate is that the gradient of a linear correlation is 0. And then you have to perform the appropriate test. For correlations, this is usually done through an ANOVA. Or if you suspect that the data are not normally distributed, then it would be a slightly different test. It would be, in this case, what is called a Kruskal-Wallis test. So be careful. I usually could not give a lot of marks if you've given me descriptive statistics for a statistical test. There is the common misconception that a high t-value or chi-square value is a measure of how different the samples are. But this is not true. You can have a fairly high t-value and still the samples would not be considered as too different. It really depends. This depends not just on the t-value, but also totally depends on the degrees of freedom. So you can have a fairly high t-value with a low degree of freedom and not reject the null hypothesis, whereas if you've got a very high number of degrees of freedom, your t-value would need to be smaller. The same for the chi-square value. So this is not indicative. A high t or chi-square value is not indicative of how different the samples are from each other. A lot of people told me that a paired t-test is derived from the same population. And again, we need to be very, very careful here how we express these things. There is, in the previous video, I showed you the data structure of a paired t-test. We have two samples basically, and although these samples are linked with each other, it does not mean that they have to come from the same population. That is exactly what the test is actually trying to address. Are these two populations the same? So when we have our data set, category 1, category 2, and we have this data set for a paired t-test, it basically asks the question, what is, not so much are these from the same population, the question is, what is the data set for the difference? And is this difference actually linked to, or is this difference the from a population where the population mean is 0. So with the same population, it doesn't really make a lot of sense in this case. So that's the paired test. Null hypothesis. Oh, that's a classic one. The null hypothesis compares the sample means. And actually, no, it does not. And I think I made this very clear in the video about the hypothesis testing. Hypothesis testing, the null hypothesis, compares the population means. Population means. mu1 and mu2. We use the samples to derive or estimate the population means, the parameters of the population, and we compare these things. Or we use the observations and compare them to a reference value. We are not comparing samples. We are always comparing the underlying populations. And that's very, very important. The p-value can only be between 0 and 1. Absolutely important, because the p-value gives us a probability that we observe the test statistic given that the null hypothesis is true. So a p-value of 2.56 doesn't make sense. It doesn't exist, because a p-value of 0 means the probability is 0, it does not happen, or p-value of 1 means it's 100%, it will always happen. Anything outside this range just simply doesn't make sense at all. Here was one that sort of made me a little bit chuckle. The t-test requires quantitative data, whereas the chi-square test does not. That's quite a funny one, because all our tests, whatever we do, all the data need to be quantitative. They need to be numbers, right? What people probably meant was that here, quantitative, we need to have continuous data, and they need to be of an interval or ratio. Whereas in a chi-square test, we also need quantitative data, because otherwise we can't compare things. I can't compare red with blue. We always need to have numbers, and that is what quantitative means. Just in a chi-square test, we use frequencies, so it could be proportions, that would be a binomial, or we can use count data, that would be Poisson. We could look at just simply frequencies in terms of observed and expected. These are the classical chi-square tests, but they all have to be quantitative. It's just different terms for quantitative. Statistical test compares a critical value with a test statistic. Yes, that is true. That is the basis of any kind of statistical tests. That is a prerequisite, actually. Prerequisite. For any statistical test, but statistical tests go further. Statistical tests then use this comparison. Use the comparison to get a probability, to get a p-value. And only once we've got the p-value and we've set a significance level, then we can make a decision. Just by comparing things, it's nice and it gives us an idea whether we should expect a null hypothesis, but a bit is missing, and this bit is the p-value. So always go the step further, not just compare the test statistic with a critical value, but then say what is the probability that I actually observe this test statistic. A lot of people believe that a z-test can only be used for very large samples, and actually this is sort of, yes, somehow it is true, but even if you've got a large sample, so if you've got, say, 300 observations, you still should not use the z-test if your population standard deviation or population variance is unknown. So z-test only if the population standard deviation is known. Likewise, people say, oh, I've got a large sample, and therefore I can use a t-test. No, technically you should not use a t-test if it is just if the standard deviation is known. If the population standard deviation is known, stick with a z-test. If it's not known, go for a t-test. And it doesn't really matter what the sample size is in this case. For a t-test, the sample must show a normal distribution. Now that sounds, on the surface, it sounds all right. We need a normal distribution. The crux is here the word sample. The sample probably doesn't show a normal distribution, or we might not even have enough observations to say, yes, it shows a normal distribution. The crucial point is that the population is normally distributed. The population must be normally distributed, not the sample. The sample we don't usually know. We don't have enough information about the sample, but it's the population. A lot of people also mixed up the notion of a statistical hypothesis and a scientific hypothesis. So the scientific hypothesis would be men are taller than women, or and people were incredibly creative in coming up with ideas. So the milliliter of tears cried before and after an exam, the grades of Bayern Munich supporters or not supporters, football practice, the effect of a drug called Clapperdoll, all these things. And that was really, it made my day. Was fantastic to read through all these examples. But these are scientific hypotheses, and they are great, right? However, a statistical hypothesis is incredibly boring because it's always the same. A statistical hypothesis, like for a t-test, would be mu1, the population mean of one population represented by sample 1 is the same as the population mean represented by sample 2. And then the alternative. For chi-square, it would be observed population equals expected distribution. That's the expected from the model. So these are the statistical hypotheses, and they are really fixed, they are boring, they are always formulaic, the same stuff. The scientific hypothesis is different. But for statistical tests, the scientific hypothesis, we don't really look at it. We just look at the statistical hypothesis. And last but not least, one of the common misconceptions is that the t-value needs to be smaller than 5%, and therefore we reject the null hypothesis. And you can very easily see, no, this is not true. It's not the t-value. So I don't know whether this was a typo or whatever it was. It needs to be the probability. So that would be the p-value. The probability needs to be smaller than a certain threshold. That's our alpha, that's the significance level. And as I said initially, the significance level can be anything. We can set it to 5%, we can set it to 10%, we can set it to 0.1%. Whatever we feel most comfortable with it. This is our threshold where we say anything above, we have no evidence to reject the null hypothesis, or if it is below this threshold, then we can reject the null hypothesis. So these were actually the most common misconceptions that I encountered, and I hope this makes sense, and hopefully you learned something. Thank you very much for watching.